In the last few videos, we focused mainly on one question. How many proton NMR signals do we get? But once you know the number of signals, the next question is just as important. Where do those peaks appear? That is what chemical shift is about. In this video, I want to make chemical shift feel logical. We are going to understand what upfield and downfield really mean, what shielding and deshielding mean, and why some proton signals appear further left while others appear further right. Left equal downfield, right equal upfield. So far in this Proton NMR series, we have already covered the basics of Proton NMR, how to count equivalent and non-equivalent proton environments, and two important exceptions involving alkene hydrogens and CH2 hydrogens next to a stereocentre. So the natural next step is this. Once I know how many signals there are, how do I predict where each signal appears on the spectrum? Chemical shift is simply the horizontal position of a signal on the proton NMR spectrum, but that position is not random. It tells us something about the proton's environment, especially how much electron density there is around that proton. So when you look at a proton NMR peak, you are not just seeing a line on the graph. You are seeing information about the electronic environment of that hydrogen. This is the part that many students mix up. So let's slow down. On the printed NMR spectrum, the left side is called downfield, and it has a higher delta or higher chemical shift. The right side is called upfield, and it has a lower delta value. The simplest memory line is this. The shielded protons appear downfield on the left, while shielded protons appear upfield on the right. Now, let's talk about shielding. Electrons around a proton act like a protective cloud, so more protected. If a proton has plenty of electron density around it, more electron density, it is more shielded from the external magnetic field. A more shielded proton ends up appearing further upfield, which means further to the right on the NMR spectrum. More shielding equal further right. So when you hear the word shielded, your brain should immediately think more electron density, more protection, more towards the right. Deshielding is the opposite idea. If electron density is pulled away from a proton, that proton becomes less protected. We call it deshielded because it has less electron density. A deshielded proton appears further downfield, which means further to the left. So if shielding pushes a peak to the right, deshielding pushes a peak to the left. This is the big core idea behind chemical shift. One major cause of deshielding is an electronegative atom nearby. Let's use bromoethane as an example. The bromine atom pulls electron density away through the sigma bonds. Because of that, the CH2 group next to bromine becomes more deshielded. The terminal CH3 group is further away, so it is less affected. That means the CH2Br protons appear further left, while the CH3 protons appear further right. This gives us a very useful rule. The deshielding effect of an electronegative atom is strongest on the protons closest to it. Closer to the electronegative atom equal more downfield. The effect gets weaker as you move further away. So when you compare proton environments, always ask yourself which proton is nearest to the electron withdrawing atom. In this case, it is HA. That proton is usually the more downfield one. More downfield because more deshielded. So the nearest protons typically feel the strongest effect. Let's try another example, methoxyethane. Here we have 3 proton environments. The protons nearest to oxygen are the most deshielded because oxygen is strongly electronegative. So the terminal CH3 furthest from oxygen is the most upfield. The 2 proton environments directly attached through carbon to oxygen are both downfield compared with a normal alkyl CH3 group. Downfield. The exact order between OCH3 and OCH2 can be discussed in more detail later, but the big idea remains the same. Oxygen pulls the nearby proton signals downfield. There is also a smaller trend that you should know. In simple alkyl systems, protons on more substituted carbons are often slightly more downfield. Slightly more substituted equals slightly more downfield. So tertiary tends to be a little more downfield than secondary. At secondary, a little more downfield than primary. But this is not the main idea to rely on. Useful, but weaker than the strong electronegative effects. Strong deshielding caused by an electronegative atom is usually much more important in beginner proton NMR questions. Let's revisit methoxyethane again. There are 3 proton environments here. The OCH3 group, the OCH2 group, and the CH3 group. The terminal CH3 is furthest from the oxygen, so it is the most upfield. The 2 proton environments near oxygen are both pushed downfield because oxygen is electronegative. Of those 2, the OCH2 signal is usually slightly more downfield. Simply because OCH2 is more substituted than OCH3. A common mistake is to jump straight into trying to memorize a long list of ppm values. That can help later, but it should not be your first instinct. Do not start with ppm memorization. Instead, ask the chemical question. Is this proton relatively shielded or deshielded? Is there an electronegative atom nearby? What is pulling electron density away? Is there a carbonyl nearby? Is this proton in a plain alkyl environment or in a more electron-poor environment? Once you think this way, chemical shift becomes much easier. Last but not least, let's do a quick recap. Chemical shift is the position of a proton signal on the NMR spectrum. Shielded protons appear upfield. On the right, the shielded protons appear downfield. On the left, electronegative atoms pull electron density away and therefore deshield nearby protons. The closer the proton is to the electron withdrawing effect, the more downfield it will usually appear. In the next video, we will take this idea and apply it to real molecules step by step.